Oh, am I good? Yes. Good. Not that good. Aha, right. So we have two questions that we want to think about. One, really, can quantum coherence even survive under physiological conditions in these photosynthetic systems, which are hot and liquid and floppy and have very soft vibrations? And we would imagine quantum coherence would immediately disappear. And it turns out that these vibrations has a time scale of 10 to 1,000 femtoseconds. So dephasing is fast, but it's not infinitely fast. Right? It's not instantaneous, and maybe something happens in these timescales which means something to the system. And second, okay, assuming that these exist, do they have some benefit to the biological system, which is, I think, kind of the essence of what quantum effects in biology should mean or initially meant. And the point was that these experiments were done in laser light in vitro, and that's very different from realistic conditions. So I'm just rephrasing the question here. This is kind of the evolutionary time, and you think about the structure of the photosynthetic complexes. So did evolution design, or someone else designed the structure of the FMO complex, having in mind that as you increase the design, you move into the Goldilocks regime where quantum coherence are important, and that increases the efficiency. So is the efficiency the driving evolutionary force for the structure of photosynthetic complexes? And this was the question we wanted to answer. And the first ideas in this field came from many, many groups, maybe originally from Caruso, and Caruso and Meyer measured this in a realistic system, but they came even before that, in Martin Plenius group and Alana Spuru-Guzig and so on. And the idea is what we call environment-assisted quantum transport, or ENACT. And the idea is that if you look at the efficiency, some measure of efficiency, as a function of, let's say, dephasing rate. So if dephasing rate is 0, you're in a fully isolated quantum system. If dephasing rate is very, very fast, you're in a fully classical system. Everything is diffusive and all the equations can be mapped into classical dynamics. And if you look at the efficiency, at some point there is a maximum. And so the idea was that the structure of photosynthetic complexes is such that the system is right in this Goldilocks regime where there is a finite amount of quantum coherence, which is just enough to increase the efficiency. And again, this effect has been demonstrated experimentally using external noise as a dephasing actor to show environment-assisted quantum transport. And what we wanted to ask is, okay, first of all, where is this effect coming from? What is the general mechanism for environment-assisted quantum transport? Can we have a universal explanation to all systems exhibiting this kind of system? And true, do photosynthetic systems really using it? And the answers to these questions are in this set of papers that goes on for a few years. Just a brief mention about methodology. Being a theorist, we go to the lowest level theory that can capture the physics that we're interested in. And in this case, this is the Lindblad equation. The Lindblad equations are very, very simple in the sense that they cram all the effect of environment into a single number, which is the dephasing rate. How fast do quantum correlations decay inside your system? So we have the so-called Lindblad equation, and this is the Lindbladian. It has in it these V operators, which effectively encode the action of the environment onto your system. So you have the Hamiltonian describing the excitation of excitons on the network, and this can be mapped very accurately for all kinds of biological systems. And then we have a Lindblad operator encoding the excitation with incoherent light. So this is not laser light, but it looks more like sunlight in some sense. And there is a sink which encodes the excitation leaving the transfer complex to the reaction center. So that's all the ingredients down. And the phasing, which of course mimics the noise induced by all the vibrations which are present in these complicated wet protein environments. But generally speaking, it's a quite simple system. And when we started looking at it, we realized that you can map the environment-assisted quantum transport into a competition, a tug of war between two effects. One effect we call population uniformization. So the idea is that when you start with a fully coherent system, and it has a source and a sink, but the pathways of excitations through the system, and as a result, the population of excitons inside your system, inside your network of exciton sites, will reflect the wave function nature of the system. And hence it will not be uniform at all, because the wave functions are not uniform unless you have a very straight and neat system. Wave functions have some structure, and this will be reflected in the exciton population. What dephasing does is flattens out the population of excitations, the populations of excitons. So in at some dephasing rate, which is strong enough, excitations are uniform across the system. Now, if you increase dephasing even more, you reach the classical limit where there's nothing but fixed law. You have a source, you have a drain, and you have a gradient going through from source to drain. And the competition between these two limits, where population uniformization becomes active, is where environment-assisted quantum transport comes in. And you can actually see it quite well if you look at a chain which does not have a symmetry. You need to break the symmetry. And here you see environment-assisted quantum transport, because there is initially a node here and a node here. There is some wave function structure. And then you uniform the population, and excitations can flow very easily until you reach the strong dephasing rate, the classical regime, and then you introduce Fick's law. This is the orange line here, and then efficiency goes down again. And if you have a fully symmetric system, then you begin with a uniform population. So there's nothing competing with the uniformization, and therefore you don't have environment-assisted quantum transport. Okay, and you can see that for various systems that we checked, as long as you have some asymmetry in the system, then the wave function structure is reflected in the original structure. You get population uniformization, and then you get to fixed law, and you see environment-assisted quantum transport. And just before that, I'll say that we did these tests also with more complicated calculations, Nakajima-Zwanzig approximation, some hierarchical equations of motion, and other people did this as well. And this kind of explanation basically holds throughout all the examples that we see. So it's a good universal explanation for the environment-assisted quantum transport. And you can trace back all the papers that were written about it before us, and you can see that, in fact, the same effect happens there, but it was not recognized. So this is really a universal explanation to what is going on. Of course, a chain of two-side systems has nothing to do with realistic systems. So the next step was to look at the three superstars of photosynthesis, which is the LH2 antenna, the PC645, which has antenna and transfer center, and the FMO, which has only the transfer center. And the neat thing about these is that we know the structure. right? The Hamiltonian for these systems is well documented. Is it exact? No, of course not. But the essence of the thing is there. So we did exactly the same calculation, making sure that the parameters we take, the Hamiltonian, the excitation rate, the positions of source and sink, all agree with what we understand about the biology. Okay? And these are the examples for PC645 and for the FMO. You see that there is an increase indeed in the efficiency. And the efficiency we can actually calculate. It's just the power out divided by power in. So it's a measure that we can actually calculate. So you can see that the physiological regime indeed lies within this interesting Goldilocks regime of perfect environment-assisted quantum transport. But it doesn't mean anything because the efficiency increase. So now you need to look at the y-axis is tiny. The effect is minute, is about 0.0015%. So honestly, this change of efficiency means nothing to the system. It's just not something evolution would worry about. At least, of course, I cannot speak for evolution, but that's the feeling that you get when looking at this data. If you look at LH2, the situation is a little more complicated because it doesn't have one source and one sink. Light comes in from all over because it's a joint antenna transfer center and reaction center. So you need to average over all possible places. And we do that and we see the same thing. When you reach the physiological conditions, you are indeed in the environment-assisted quantum transport regime, but the enhancement of efficiency is essentially nothing. Doesn't mean anything. So the conclusion is that is photosynthesis using quantum coherence to enhance efficiency? Probably not, which was the title of the paper. And maybe some will think that it's a bummer, but this is what the results are, right? I was hoping for a different result, but that's what we got. But then we started playing around. Of course, we have a code you can play around, and you can, for example, start tweaking the positions or the connections and the transfer matrix elements between the sides of the excitons. And what you see, I have lots of time. What you see is that in the Goldilocks regime of an act, they are all the same. The system is oblivious to changes in structure. However, if you're in one of these regimes, you can see that small changes make a big effect. And you can, in fact, there is an upper limit to the efficiency, but there's no lower limit. If you're somewhere around here and you change the structure, you can decrease the efficiency by many orders of magnitude. So this is one thing maybe that quantum coherence do achieve. They put the system in a position where excitons are spread all over, and therefore small and even large changes in the structure do not make a big difference to the efficiency. And this is an interesting thought because this relates to what Naama mentioned earlier about stability. And when you ask a biologist, what do plants care about? The immediate answer is stability. They don't want changes. So maybe this is a mechanism not to enhance efficiency, but to enhance stability. And this is the idea that we were promoting in this work. And then we started looking a little deeper into LH2. So LH2 is composed of two sets of rings, which are kind of modeled here. It has a backbone of carotenes and a scaffold of lycopenes. These are biological molecules. I'm a physicist. Please don't ask me more details about them. To me, they represent a graph. Okay? My ignorance is that deep. But interestingly enough, Rajivin et al., and this is a citation of a very, very nice paper, which went, I think, under the radar for the community. They did a very, very beautiful experiment. What they did is shine light and measure the emission through LH2, but they did it in a smart way. In one measurement, they excited the lycopenes and measured the excitation from the bacterial chlorophyll, from the main bulk. And on another experiment, they, here they excited the bacterial chlorophylls and looked at the emission from the lycopene because they have different bands. So you can tune your instrumentation to check the emission from that specific structure. When you excite the bacterial chlorophyll and measure the lycopenes, you see tiny effect. You see emission of about 5%. But when you go the other way around, you excite the lycopenes and you measure from the bacterial chlorophyll, you see 50%. And then their argument was something like, well, it looks like there is a blockage of exciton transport from the lycopenes to the bacterial chlorophyll. No, but that doesn't work. But because if there's blockage goes both ways, right? If the blockage is in the tight binding elements of the Hamiltonian, then it's there. You shouldn't see anything. So this was a puzzle that we were thinking about. And what Elinor did was take the exact structure of LH2, plug in the same formalism, excitations, source sink, you average over disorder. And what we find is something quite interesting. If you look at no dephasing, right, you excite from the bacterial chlorophyll, you get most out of the chlorophyll, but also from the lycopene. And let me not go into the details. Basically, what you can see is that depending on whether or not you're in the quantum, classical, or Goldilocks regime, you will find something very, very different. And only in the physiological Goldilocks regime, we get numbers which are quite similar to the experiment. And the explanation has nothing to do with blocking the energy channels. It's actually the other way around. When dephasing is in the Goldilocks regime, so you have population uniformization, then all the excitation states are excited, whether or not they belong to the scaffold of the bacterial chlorophyll or to the lycopene itself. They are all excited. However, as it turns out, many of the states in the lycopene are dark. They do not emit. And only a few % of them are actually bright and can emit light. So you are populating all of them, but they are only emitting from a few. And this was a way, first of all, to reconstruct the experiments. Of course, these are 2 data points, but we are in the ballpark considering the fact that it's a very, very, very crude model. And in a way, this is a way to probe the signature of quantum coherence in a very simple experiment. I remind you that the original experiments, which were already discussed in the first talk today, in the second talk today, were complicated, these 2-dimensional spectra. These are very complicated measurements. And this is a very simple measurement. You excite and you measure. There's nothing complicated about it. And even in this kind of experiment, you see the signature of quantum coherence. So that's very nice. The second point is, okay, so the first point is that we understand where environment-assisted quantum tunneling is coming from. It's coming from this tug of war between population uniformization induced by dephasing and classical gradients. Real photosynthetic systems couldn't care less in terms of efficiency, but maybe in terms of stability. But the idea is that if everything is populated, then when you shine light in the wavelength that can be captured by the lycopene, some of that excitations reach the bacterial chlorophyll. So you're opening another spectral window for the plants to use, which would not be there if you are either in the fully quantum or the fully classical regime, because they can exploit light who's coming from any parts of the sources that can absorb light in the system, because all the population is going to be uniformed anyway. It doesn't matter where the excitation came from, all the excitations are going to be popular. Some of them are going to reach the sink, the chemical reaction center. And this is kind of the idea that maybe a quantum coherence is not used for energy transfer efficiency, but rather to open new spectral windows to absorb light better. And I'm turning to the community here. This is an avenue that can be explored experimentally. And the quantum biology community, as we heard in 2 talks ago, is having trouble communicating between theory and experiments. Experiments are really hard. And I think this is an avenue which can be explored, and I urge you to try. And with this, I think I'm done. Thank you for your attention.